Hello, welcome to another module of this course, analog circuits. So, we have been talking about various nonlinear circuits over the past few weeks, and in this module we are going to introduce you to another nonlinear circuit which is very popular, and this circuit is known as the rectifier. So, a rectifier is a circuit that, putting it simply, converts an AC voltage to a DC voltage. So, basically what we do in a rectifier design is that we allow the voltage to conduct or to pass through in one half cycle and let it just not pass through in the other half cycle. So, this is the simplest construction where only the voltage is allowed to pass through in the first half cycle, and the other half cycle we do not allow the voltage to pass. So, that is the principle of a half wave rectifier. In this module we are going to study about other circuits which allow voltage to pass through in both half cycles, but in the other half cycle they invert the half cycle, thereby making the sense of the voltage at the output the same for both half cycles. So, let us see those circuits. So, ideally, if suppose you have an AC signal like this, you should get an output, and let us say this is the RMS voltage. Then you should get an output which is like this. So, Vrms is the root mean square voltage and after rectification, the output should ideally be equal to Vrms, but that is never possible. That is never possible because there is no ideal rectifier which can do such a conversion, but we can approximate it or go nearby. For example, this negative half cycle of the input sinusoidal voltage, if we can flip it over. So, if we flip it over, then we would get something like this. So, after flipping over, we get something like this. So, you see the negative half cycle here now has become here. So, this is my V out. So, this is also a form of rectification because now all the voltages at the output have only, they have no negative component, they have only positive components, and so though not equal to the ideal, they do approximate DC. Of course, a DC voltage which kind of varies slightly with time. So, this is the principle on which we are going to design our rectifier circuit. So, the first type of rectifier is known as what we call the half wave rectifier. As the name suggests, this rectifier only allows half the sinusoidal voltage, only a half cycle of the sinusoidal voltage to pass through it. Okay. It does not allow the other half cycle to pass through it. So, the circuit for this is now usually if we consider an ideal diode, then of course, our rectification will be like this. So, for an ideal diode, the resistance R d is equal to 0 and the threshold voltage is also equal to 0. Okay. So, for such a diode, this is what will happen. If this is my input, this is what my output will be. But in real diodes, where we have a finite value of R d and V d 0, the characteristics of such a diode will be of this form. The Vi characteristics, that is. So, the circuit, corresponding circuit is like this. This is Vs. Okay. The slope of this line is given by R upon R d plus R. So, with this kind of, here is my V d 0. Okay. And suppose my input, if I draw it on this way along the y axis, then it should touch here. So, then the output that I will get will be something of this sort. this is Vs, and this is what the supply voltage is, and this inner curve, this is my actual output. So, this is V 0, okay, and the spacing between the peaks of Vs and V 0 is V d 0. And of course, after this we will again get a 0 voltage, and then finally after some time we will get again the repetition of this curve. So, this is how it will repeat, okay, this curve. So, my output, if I use a blue marker, output will follow like this. It will go here, follow this, come down like this, follow up and like this. So, this blue curve, this gives my actual output voltage when I consider the presence of this threshold voltage V d 0 and also a finite resistance, diode resistance R d. In order for us to rectify the circuit even during the negative half cycle of the input, we need to modify the circuit, and the circuit we obtain is known as a full wave rectifier. The circuit for that is given like this. So, here this part which was not present in the circuit for the half wave rectifier, this is actually a transformer, this whole thing. Now, the transformer does not really play any role in the rectification, but it is necessary to show it, show this element just to let you know that there are actually two sources, plus minus Vs and plus minus Vs. So, the transformer takes in an output, and after up conversion it produces two different outputs, which are our actual source inputs, Vs and Vs. Okay. So, each of these small windings in the transformer will produce plus Vs voltage output, like shown like this. Now, how does this circuit operate? Say we are in the positive, let me draw this circuit. Say Vs is positive. So, then okay. So, this is T, this is Vs. Okay. So, when this is, say this voltage is positive, Vs is positive, then or in the or we are in the positive half cycle of Vs, this diode D1 will be forward biased, and when Vs is above the threshold voltage of D1, this will start conducting. Okay. When Vs is in the positive half cycle, however, diode D2 will be reverse biased and will not conduct. So, the voltage Vs will therefore appear across the resistance R0, that is, it will appear across the output voltage V0 during the positive half cycle. In the negative half cycle, D2 will be forward biased, D1 is reverse biased. Therefore, in the negative half cycle also we will have Vs appearing across the voltage V0. So, now ideally if our diodes were ideal, then we would have simply, our output would simply reflect the input. But since our diodes are not ideal, and if we consider both the negative and positive half cycles of the input voltage, then the output characteristics of this diode will be something like this. Sorry, this is VO and this is Vs. Yeah. So, it will be something like this. The slope equal to 1, here the slope equal to minus 1, this is minus Vd0 and this is plus Vd0, where Vd0 is the threshold voltage. And suppose we have input sinusoidal voltage like this. Okay. So, this is my Vs, this curve I have shown it here, okay. Slightly exaggerated version of this one. Now, here the slope is 1 because we are assuming that the internal resistance of the diode is equal to 0. So, if this is my Vs, which I have drawn along the y axis, which is in this graph is shown along the x axis, then the output that I will get is something like this. Let me use the blue marker. Okay. So, my overall output will be as shown by the blue marker. Just like just like the previous case, we will have a diode drop Vd0 between the supply and the actual output. Fine. Now, an important parameter in determining the success of any circuit, of any rectifier circuit, is known as the peak inversion voltage. I am calling it is important for the success of any circuit, of any inverter circuit, because peak inversion voltage gives us an idea about what is the maximum voltage that a diode is subjected to when it is present in a rectifier circuit. So, in this case, if we go back to our circuit for a moment, the full wave rectifier, any of these diodes will experience the maximum voltage across their terminals when they are in reverse bias mode. In the forward bias mode, it is conducting, the diodes are conducting, therefore, the voltage drop across the diode will be same as the threshold voltage, but it is in the reverse bias mode when the diodes face the maximum voltage across their terminals. Now, suppose D1 is conducting, that is Vs is positive and D2 is negative, is in the reverse bias mode. So, what is the maximum voltage that D2 will be subjected to? So, here we have minus Vd0, right, and here we have 2 Vs, right. So, the maximum reverse bias voltage across D2, I can write this peak inversion voltage as 2 Vs minus Vd0. What about the case for a half wave rectifier? If we can go back to the circuit for a half wave rectifier for a moment, what was the maximum voltage that this diode D that it could experience in the reverse bias mode? So, peak inversion voltage for this diode will be equal to Vs, which is the supply voltage. Okay. Since we do not have any diodes conducting in the reverse biased mode, so the peak inverse voltage is equal to Vs. Now, this is a problem of this kind of full wave rectifier circuit. If our Vs is very large, then there is a risk that the diodes can break down, and therefore, to avoid that, we always try to reduce the peak inversion voltage. So, one circuit where we are able to do such a where we are able to do a full wave rectification yet reduce the peak inversion voltage is what is known as a bridge rectifier. So, a bridge rectifier has a circuit as follows. So, again we have a transformer which supplies a voltage of plus and minus Vs, and then we have a bridge circuit. So, the bridge circuit consists of 4 diodes connected as shown. Okay. And the principal operation is similar to that of the full wave rectifier. See, during the positive half cycle, this say when Vs is positive, then D1 and D2 will be forward biased, and during the negative half cycle, D3 and D4 will be forward biased. So, overall the output, input and output relationship will be something like this. So, the shape of the curve is similar to that of the full wave rectifier, but the difference between the two peaks of the input and output is now equal to 2 VD0, because of the two diode drops that we have to, that the input. So, this is my input, my output by the way is taken between these two ports, okay. It is taken across the bridge. So, every time we take the output we have to undergo two diode drops, and that is why the difference between the peak of the input and the peak of the output is 2 VD0. However, what about the peak inversion voltage? Now, let us consider the case when diode D3 and D4 are conducting. Okay. Then what is the voltage across this diode, say? So, the voltage across this diode D1 can be considered to be equal to V0 minus 2 VD0. So, this is, sorry, I just want to correct it. So, we have V0 equal to 2 Vs minus we have V0 equal to Vs minus 2 Vd0. Yeah, just note this correction. And the voltage, the reverse bias voltage across this diode D1 is equal to V0. Okay. Suppose we are taking, so this is my positive, this is my negative, this voltage plus the voltage across this transistor D4. Okay. So, I have Vd1 equal to V0 plus Vd4. The voltage across D4 is equal to the diode drop, isn't it, Vd0. So, this will be equal to Vs minus 2 Vd0 plus Vd0, which is equal to Vs minus Vd0. So, what we see here is that for the bridge rectifier, the peak inversion voltage is equal to Vs minus Vd0, which is much less compared to the peak inversion voltage for a full wave rectifier, which was equal to 2 Vs minus Vd0. So, that is one big advantage of the reverse of this bridge rectifier, in that the diodes do not break down easily. The disadvantage of course for this bridge rectifier is that the difference between the peaks of the input and the output is now 2 Vd0 as compared to Vd0 for the full wave rectifier. So, in this module we covered some topics on rectifier design. There are some variations of this rectifier designs as well, something known as a peak rectifier, and then and of course there is the problem of threshold voltage. As we are seeing in all kinds of rectifiers, the output never matches the input. There is always the diode drop present between the output and the input. So, to get rid of this problem, we have some special circuits known as super diodes, where this threshold voltage problem is removed. So, that is also something we will be covering in the next module. Thank you.